Thank you very much, and thank all of you for attending today's webinar on what's new in March 2017. I'd also like to thank those individuals who participated in the beta testing to make sure that this is a high-quality release. All of our releases, we always try to address certain themes: improving the material behavior modeling, which is very important for newer materials, improving contact both in terms of the technology and the ease of use, general ease of use improvements associated with MenCat, whether or not it has to do with performance or meshing enhancements, and improving the performance of the Marc solver, and advanced analysis topics including adaptive meshing. So I'm going to start right off in terms of material behavior and material data fitting. A quick summary of what we can do in terms of taking the data that you obtain from experimental tests and generating the coefficients that are required to perform a simulation. Of course, we can do this for rate-independent large-strain elasticity, typically the Mooney-Rivlin material model or the Ogden model or the Gent model or the Boyce model. Or we can incorporate also damage as well into these models. And we can treat viscoelasticity. We can obtain the coefficients either based upon time domain type analysis or frequency domain analysis. We can incorporate nonlinear viscoelasticity, which is usually done through the Bergstrom-Boyce model. We can incorporate frequency-dependent damping and frequency and amplitude-dependent damping, the so-called Payne effect. And now with the Marc 2017 capabilities, we can take experimental data that incorporates large-strain elasticity, viscoelasticity, permanent set, or what some people consider plasticity, and damage, and obtain the necessary coefficients for the parallel rheological framework model that we introduced in 2015. We can also have some new material data fitting capabilities for metal plasticity, for flow stress, and for anisotropic plasticity. And in fact, we're going to start the discussion with those models themselves. So before, when we had material behavior and it was function of the plastic strain or the equivalent plastic strain and the strain rate and the temperature, one could enter these as tables, or of course you could have entered them as a user subroutine, and Marc would do a piecewise linear representation of this. We introduced some models over the last few years, but now with 2017, we allow you to enter table data, and we will fit the coefficients to any of these models. So if we would see this line in green, that was the original data, and red was using the Kumar model, and black was using this GMP2 model. We can see how these numerically evaluated models represent the experimental data. And in fact, often it's useful to use these numerical models because they result in less iterations and less computational cost in the simulation compared to piecewise linear data. And what we can do with these models is you can always determine which model best represents the experimental test data that you have. So here we entered a single table. It was only strain-dependent data, and we asked to fit the power law model, and we see this correlation in red. But if we would have taken the same experimental data and used the Hockett-Sherby model, we see we have really perfect correlation between the experimental data and the numerically fit data. For more complex input data, let's say if you have both temperature dependence and strain rate dependence, you might want to use something like the Johnson-Cook material model. And here you can see is we have multiple families of data, and we have some pretty erratic data. So one of the nice things about this method is you don't need to have a regular table. So, for example, temperatures, it's likely that you have less experimental data than you do at low temperatures, and they don't need to be regularly spaced. Instead, we can do what we use called ragged input data. So you can see the particular curve fitting that's been done, or if we zoom in on one particular model, one particular set of experimental data at one temperature and one strain rate, we can see what the correlation is. We've also introduced some capability for dealing with anisotropic plasticity. This is generally for materials that have been rolled, whether or not it's steel or aluminum. We've had some of these models. Hill model's been around for a long time. The original Barlock is a newer model, and then we added some additional models a few years ago. But it was very difficult to go from your experimental data to the coefficient. So now what you can do is you can perform your experiment. You can take your rolled sheet and cut out different slices at 0 degrees, 45 degrees, 90, or hopefully more locations if you want to fit one of these more advanced models. And what we'll do is we will fit that data so you can see what your non-elliptical type yield surface looks like associated with these more advanced models. The parallel rheological framework model was really introduced in the 2015 release, but it was challenging to use because of the number of coefficients. This is really for materials that are rubber materials, could be carbon-filled rubber materials, or plastics, or thermoplastics, materials that show damage and effectively show some permanent effect. So for these types of materials, it's important not just to do a uniaxial tension curve, actually best to do cyclic data, cyclic testing at different strain rates and at different magnitudes of the stress so that you get a full series of data. And we get this data not only for uniaxial tension type behavior, but also for biaxial data. So what this parallel rheologically framework model gives us is it allows us to represent the material by a primary elastic model, which can be either large strain or it can be small strain, a viscoelastic model, which is really of the type Boyce, a plasticity model, which is basically looks like a von Mises plasticity model. So you might notice that these are all really isotropic behavior, and a damage model as well. And you can have multiple terms of the viscoelastic behavior, the elastic plastic behavior, damage behavior. So we take a look at something like the thermoplastic material, and effectively, again, the green model is effectively the experimental data, and the red model is effectively the curve fitting that we obtained from using this particular model. So we would do a finite element model test with Marc, and we did duplicate that experimental process of taking a rod or a 3D brick and running this type of deformation history. We would effectively get the curves that looks in red. It would be identical to what we obtained from the curve fitting. So it's very easy to do. You would specify your table. In this case, it's a ragged table. We'd have time as the independent variable, strain and stress is the dependent data, and we would have selected all the different models. That's here a Mooney-Rivlin model. Only a single term Boyce, a single term plasticity model, and it would have calculated these coefficients. And the more series you would have had, the more coefficients you would have effectively. Here's basically using the same model, but in this case it was a material that was effectively, this curve is at a higher strain rate, this curve is at a lower strain rate, loading and unloading, and really effectively doing a Bergstrom Boyce viscoelastic model representation using this numerical fitting technique. So it's not only work that we did in material characterization in terms of material data fitting, we've also done some work in terms of utilizing your material input, and you can put it in a particular file. You can save all your material, your isotropic or your Mooney, all your tables, whether or not they're temperature-dependent tables, and you can place them into a file. You can basically have multi-physics representation of the material behavior in that file. And then what you can do is you can use that in your organization to make sure everybody uses a consistent set of data. You can also take that data file and encrypt it. And when we encrypt it, what it allows us to do, allows OEMs to provide material data to their suppliers so that the suppliers also are using a consistent set of data, but not necessarily giving away any intellectual property. It also works on the opposite side. You could have a company that is creating the material and it wants to provide the coefficients of their material without saying everything about the material, and they too could make a file, encrypt the file, and send it to other organizations. These files can be done so that they are encrypted for a particular organization, and you can give an expiration date. For example, you might say, well, after 2 years, I have a new supplier, so I don't want people to use this particular material data. Or you might say that after that 2 years, I might have different experimental testing procedures, so I might have better data. So it allows, again, the whole group, the whole organization, the enterprise, to use a consistent set of data in the analysis. So if you get one of these text files, material data files, I should say, they can be in one of two natures. One is you can have a file with a single material in that file, or you could have a file with multiple materials in the file. So if we have a single material, we would tend to do something like, say that we're going to read in a data file. We specify the data file, and then we specify what elements or what solid bodies are represented by the material data that's in that particular file. Similarly, in this case, we are at a higher level, we're at the jobs level. We would basically say, I want a large number of materials to be applicable from this particular file. And here we specify a UME file. The E stands for encryption. And then it would take all the material data from that file and use it in your simulation. You would not see the coefficients in your Marc output, and you would not see the coefficients in any user subroutines if, in fact, it's an encrypted file. The other thing that we did for material damage is we've modified the Lemaitre damage model. Very often in damage modeling, the results are very dependent upon the finite element mesh size. So if you would change your mesh, you would get a different damage indicator. That damage indicator, if it's the Lemaitre damage model, is utilized to modify the Young's modulus and the yield stress, and so you'd end up with different results. So in March 2017, we've introduced a new procedure. It's what we call a non-local equivalent plastic strain, And what it's done is we basically do the structural analysis, we calculate the equivalent plastic strain, and then we use a diffusion procedure to get out this new non-local. So if we would take a look at some analysis, and this is part of a larger model, and if I look at the equivalent plastic strain in this non-local total equivalent plastic strain, the values in the non-local procedure are smaller. So the scale is the same, but I don't see any bright yellow over on this side. And also the gradients are lower. So we would look at an analysis of this hole in place, larger area, and we look at different number of degrees of freedom. We look at the equivalent plastic strain, the maximum value, and as we put in more and more elements to the system, we get a higher maximum value. So we're going to get higher damage. And effectively, the difference is somewhere around 10%. And if we look at this non-local plastic strain and look at it as a function of the number of equations in the system, we see that A, it converges to a particular value, and the difference between this value and this value is like 1/100th of 1%. So it converges to a nice value, and so it removes the machine, the mesh dependency associated with the damage. And we can see this here for the two particular models. It's actually a 5x5 mesh around the hole, and then we divided it by each element by 4x4 and then by 16x16, and we see we really get identical results on the reasonable size meshes in terms of the force history when effectively necking is occurring far because of the damage. To activate this, you basically enter a non-local length parameter that's going to influence this diffusion, and you activate this non-local path. So we'll do a structural analysis, and then we'll do effectively diffusion analysis, but the diffusion analysis is very, very fast compared to the structural analysis. Of course, contact is very, very important for all of our users. And in March 2017, we really did three things, but I'm going to really talk about two of them. One has to do with the ease of use. And the ease of use enhancement in March 2017 is that we have basically tied the colors that you see associated with bodies to the actual body. So if we would have had this geometry, and you might be familiar with that geometry from seeing an Apex webinar. This is a landing gear door. There are quite a few bodies associated with it. If you would have removed some bodies or parts from the visibility, the colors would change. And in March 2017, the colors do not change. And in fact, that color is provided to Marc. And then when you do post-processing from the Marc post file, you get identical colors to what was in your original Mentat model. If you don't like the particular colors associated with Mentat, what you can do when you define your contact body properties, you can basically edit the color and change the color to whatever suits you. This is really important when we look at the contact table, especially the contact table option when we have a large number of parts in the model. So if we had more than 15 bodies, remember we have to scroll. We have to hit the 16 to 30 and 16 to 30 here, and we would suddenly not remember what our body names are. So now what you're going to see is you're going to see the same colors as what you're going to see on the display, independently of what you have in terms of visibility. And it's going to be much easier for you to define the contact tables. For example, on this cracked camshafts with the connecting rods and the pistons as well in the model. Another thing that people have asked us was, can I see what is the actual contact area, the interaction area between bodies? So quite a bit has been changed in March 2017 so that we not only look at post-processing from a body perspective, but from an interaction of the body perspective. So if you use segment-to-segment contact, what you could do is you can now get a time history of this interaction of the areas. These would effectively, as you can see, been two different pairs between the rubber and below and the rubber and upper, and this information is also printed in the Marc output as well. You can also effectively get the flux that has been transmitted, again, on a contact pair by contact pair basis. This is available either for node to segment or segment to segment contact, and you can also get the force across. So the flux is very important to really see what is the energy flow in the system. The force is often very important, again, to kind of see the load transfer between different bodies in the contact simulation. So all this information basically meant we had to do a couple of things. One, we had to change the Marc input format. Talk about that a little bit later. It's going to be input version 13. And we also have to change the post file format. And before, what we often had to do when we made a history plot, let's say of the force on a particular body, we had to do a lot of scrolling. So we've changed the history plotting menus. So you would just say something like, I want to plot global variable time, which is now the default, against some value associated with this global body. So contact body, here we just select the contact body, we ask for the strain energy. We can now get many more quantities on a body-by-body basis, and we add a curve. And if we wanted to change the new contact body, we would just click new body and say add a curve again. And if we close the post file and open up a new post file, all these conditions will be saved as opposed to having to do all that re-scrolling operation again. So it's easier to look at a single result. It's easier to compare different results. We've also introduced something called looking at the contact interaction based upon particular nodes. This is really for visualization. These nodes are not associated with the body. They're just so that we can visualize something. So here's my little model. It's got 5 different contact bodies in it. We can see that the model scale is the same as the contact table. We assign 2 particular nodes to this case. And when we do, let's say, a visualization of the deformation of this body, we can say, also give us the interaction force during that process, and it will report that. It will make my little arrow plot at the nodes that I asked for. So this is quite useful if you just look at a single body. What you'll get is effectively a free body diagram of the contact forces on this particular part, which is very useful in the aerospace industry. One of the pieces of technology that we added for the Marc 2017 release is thermally driven contact. So normally we think about contact, it's based upon position, and whether or not it's conventional contact, meaning that you can have separation and slip between bodies, or glued contact, where we have no separation and no slip, that was based upon the user input. That condition of whether or not we're conventional contact, or glued contact, is now driven by the thermal behavior. And there really are two cases. One is where we want to go from conventional contact to glued contact. So you can think about I'm doing some welding operation, or I'm melting two materials together. I heated a particular temperature. I want to bond these together. Or you might want to think about the opposite case, that initially things were hot, high temperature, and then the temperature went below a particular temperature, so effectively the glue hardened, and then I would basically say it's bonded. On the flip side, you can do the opposite. You can say that break from glued contact to conventional contact based upon these particular threshold temperatures. It's available for both node to segment and segment to segment contact. It's available both for continuum elements and for shell elements. So as an example, in the thermally driven bonding, let's say this scale represents the time. Initially, the temperature is below my critical threshold temperature. I use conventional contact. It exceeds the value. I then go into glued contact. And this process is considered irreversible process. So once I'm glued, even if I drop below that temperature, I remain glued. The opposite is also true. I might have been glued at a low temperature. I exceeded the temperature. I would break the glued condition, so I would allow separation or sliding. And again, if it went down again below the threshold, it would remain the same. So this is an example of the welding problem, but our basically welding element is moving in this direction. Initially, my plates were in geometric proximity, but everything was cool. As things heat up, we go into the contact status changes from conventional contact to glued contact. So one of the things we've introduced in March 2017 is we've introduced a new contact status, which is 1.5, which represents a glued contact, as opposed to the 1.0, which represents a conventional contact status. So normally you can think of a 0 contact status, no contact. 0.5 represents near thermal contact. 1 is conventional contact. 1.5 is a glued contact, and 2.0 is a symmetry contact. So here's an example of basically I have these two pieces. They were initially glued, and this very tip gets very hot, and then effectively it breaks away when it hits the threshold temperature of 1500 degrees. So easy to do from an input perspective. Effectively on your interaction menus, you'll see things that say, okay, when should I be bonding? Should I bond above a temperature or below a temperature? What is the temperature? When should I be breaking? Should I break when I'm above a temperature or below a temperature and a temperature? Finally, on contact is we added some improvements on the output of contact. It used to be that sometimes you said, I want information, and you'd say contact, and you get a tremendous amount of information, way too much information. So now you can select using the contact body results, define which bodies you want this additional information on the output, and you can even control it on a node-by-node basis to reduce the amount of output. Of course, in March 2017, we obviously have fixed whatever problems that were reported to us since the previous release to improve the convergence of the solution as well. In the area of adaptive meshing, we've really done two things. One is we've added higher order elements for global adaptive meshing. This is useful to improve the representation of the geometry. It's also useful for problems that were highly bending oriented, because before we were effectively using the standard tetrahedral element, or of course the enhanced tetrahedral element for incompressible behavior. And it's also important for thermally driven problems where the lower order tetrahedral elements are not that good. We also did some work in improving the surface definition. So first I'm going to show an example with higher order contact for a rubber problem. So effectively we have rigid surfaces here that are real quadratic surfaces. So now effectively when we do this model, we get very good accuracy and very good representation of the contact condition, either here or in these bottom fillets as well. So the job actually runs better in terms of a convergence and in terms of accuracy. This can also be used for metal forming problems like this tool indentation. I should always caution though that when we use higher order elements, we have a mid-sized node. It's likely that we get inside-out conditions. So in fact, you might be doing more adaptive meshing steps. But what you'll be able to do is you'll much nicer capture the curvature associated with your tool, in this case, a punch. Also, this is useful for fracture mechanics problems. Here we've been talking about the last few releases. We have very nicely refined meshes in the vicinity of the vicinity of the crack tip. Here we have effectively lower order elements. Here you can see that we have higher order elements in the model. All these regular meshes are very important for fracture mechanics, because what we want to do is we want to accurately capture the stress intensity factor, because we're going to use that stress intensity factor for our fatigue evaluation as well. So we see here the red is the analytic, and using these nicely refined meshes, we can accurately capture this type of behavior. And again, in terms of utilizing this information and associated with Farrett's law, we can also get very good agreement with the analytic solution. Remember, and fatigue analysis is very sensitive to the coefficient associated with Farrett's law. This is being applied to complex problems such as this. And again, you see a very regular finite element mesh tracking the crack point, the critical crack area during the crack propagation, where initially we had initial cracks of this size, and we see the propagation. In the element technology, we've added a new family of elements. They're pyramid elements. It's a 5-node and a 13-node pyramid, both lower order elements and higher order elements. And the reason for these elements is to provide a transition between tetrahedral elements and hexahedral elements. And it's important to understand these are not a conventional hexahedral element that has been reduced to a prism element or to a pyramid element. It is a new element, its own interpolation functions, so that we do not get a singular field in this area. The elements can be used for either conventional materials, and they can also be used for incompressible type materials. I should warn you though, the subdivide is not available in MedTech. That's not so important, because usually these elements are done with automatic mesh generation, and also local and global adaptive meshing is not available with these elements in the Marc 2017 release. So associated with these elements are a new set of mesh generators. We call this the hybrid mesh generators. The hybrid mesh generator can be used either from a solid, a parasolid solid. So we read in a CAD model, it could be a CATIA model, it could be SolidWorks. We can generate this hybrid mesh from that. Or what you can do is you can take that model and first generate a quadrilateral dominant mesh on that model. So when we generate a solid model, what's first going to happen if we do this from a solid model, it's first going to generate triangular elements on the exterior surface. So we're going to get initially tetrahedral elements, then we're going to get prism elements, and then we're going to get hexahedral elements. And if we generate a predominantly quad mesh, then effectively what we're going to get is we're going to get predominantly pyramid elements and then hexahedral elements. Where there were triangular faces, we'll see tetrahedral elements, then prism elements, then hexahedral elements. So if we cut through these different approaches, you can see what we generate always all three types of elements. And here, even though the mesh is a cruder size, even if I would have made this a finer size, we would have gotten less hexahedral elements in this approach than when we started with the surface mesh. So you might say, well, how good are the pyramid, the prism elements? The prism elements are good, but there are not that many of them from a volume perspective. We really want the bulk of the volume to be hexahedral elements. Not only are they high-quality hexahedral elements, but it also means that there are less degrees of freedom in the system, so reduce computational costs. So I need to turn off my laser pointer for a second, and then what we'll do is we're going to cut through this geometry and think about that color as the hexahedral mesh, and you can see where we have hexahedral elements as we move through the volume. Another piece of element technology that's in the Marc 2017 release has to do with piezoelectric materials. So in this particular case, what we're seeing is we're seeing an ultrasonic motor, but piezoelectric materials are used for transducers. They're actually used in your barbecue grill to cause a spark. We had previously, we had lower order piezoelectric elements, but we've now added higher order piezoelectric elements as well. That gives us a better representation of the bending behavior because piezoelectric elements are often used in very thin layers. Area of multiphysics, we did some additional work for coupled thermal structural magnetodynamic analysis, where in such problems such as induction heating, we usually have a large mesh around this particular region, so we had a big model. But the magnetic field in that region doesn't change as frequently as the temperatures change and the structure changes. So what you can do is you can control the frequency of these passes. We could actually do this before in March 2016 just for thermal structural problems. So sometimes you had a problem undergoing, a material undergoing phase transformations where you needed to do the thermal problem at a higher frequency than the structural problem. And the structural problem, because it has more degrees of freedom, is more computational cost. So you can influence the frequencies of doing different passes. The area of computational performance, we've done really two things. One is on the Paradiso solver, which I certainly recommend for parallel processing. We've added the ability to see the singularity ratio. So we worked with our partners Intel, and we can now capture the singularity ratio if it is a real system and it's a positive definite system. As soon as the system becomes non-positive definite, We cannot accurately obtain the singularity ratio, and we don't print it. The other area is having to do with the MUMPS solver. And the MUMPS solver, both we've added a out-of-core capability or improved the out-of-core capability. And we've done a lot of work of using the MUMPS solver in conjunction with domain decomposition modeling. So this is really for very large models, and usually large models that are solved in a distributed memory environment. So previously, in March 2006 and earlier versions, when we used DDM and MUMPS, and the first part is true for DDM and other solvers as well, what we would do is we take our elements and we distribute them over different processors. We assemble the different element stiffness matrices. And then what we would do is we'd form a global stiffness matrix on one processor. So that meant we needed a lot of memory on this processor. And then we would distribute it back out to these other processors. So we had more memory here and more I/O because of this distribution. And with Marc 2017, we do the same thing. We form the stiffness matrices on the different domains. But we never form a true global stiffness matrix. We immediately go to the decomposition procedure on each one of the different CPUs. And this is all done using the MUMPS technology. So if we would have thought about doing this model, and this is an engine block model, it's 2.5 million elements. It has about 10 million degrees of freedom in total. Lots of different contact bodies. It's typical bolt loading problem followed by thermal behavior. And before, what you would have needed is you would have needed 160 gigabytes on one processor because we formed that global matrix. And now what we can do is we can use multiple computers. We can distribute the amount of memory requirement. And if we use the out-of-core, we even reduce the memory requirement again, so we would only need 20 gigabytes per processor. We can also see the difference between in-core and out-of-core is very, very small, and that the total wall time does a pretty nice job. It's about 3.5 times faster on this 8-processor model, and if we had a bigger problem, the parallelization would be even better than that. Finally, let me talk about some other ease of capabilities. Perhaps the most important to people is multiple levels of undo. So the multiple levels of undo is not a default in Marc 2017. So what you can do is you can change the initiation of Marc by effectively modifying the Mentat startup script, or multiple undos in Mentat by saying multi-undo equals on. The default level is 10, but you can set it to any number up to 50. I tend to find that usually I only make about 5 errors, otherwise I've probably lost what I'm doing. But you can set that as well. We have some backup files of your database. The default is it goes into your home directory, but you can assign it to a different directory as well, especially if you have some solid-state disks on your system. The other thing is we now allow long names. A lot of this has to do with this material database, but in the default mode, whether or not it's a geometry or a material property or a boundary condition or a contact body name, the names can be 128 characters long. Of course, it's hard to put that on the menuing system, but if you hover over your name in the model browser, it will then expand the name out to all these characters. Probably most relevant for material models, but also important sometimes when you get big CAD assemblies, they have very long file names. We've also closed the circle between the world of CAD and the world of analysis. So now the CAD model can be effectively seen from the simulation. We don't really ask for a solid license when we run Marc, but we know that such a CAD model exists, and we can see even in a post-processing mode, we can see the CAD geometry. Because when we look at things in post-processing, MenCat will know that it came from this particular CAD body, and it will associate it with the post-process operation. So a quick little example of this. I know it's in 2D. This was a problem that effectively had wire bodies and two sheet bodies. And effectively, this is still in pre-processing mode. We can either view things from a contact body perspective or from a solid geometry perspective. And then what we can do is the first one was in terms of the contact bodies. Here it's in terms of, first one was in terms of the CAD bodies. Here it's in terms of the contact bodies. And then also in post-processing. So in post-processing mode, we can say, look at both the finite element entities, but also look at the CAD entities. Another nice thing you'll see here is the materials information, not the data itself, but knowing which element or which body has a certain material is on the post file. Or geometry information is, there, just the material information is on the post file. So you can do a select in post-processing mode on material IDs or in terms of geometry IDs. Finally, these changes really require changes to the Marc input. All of your existing Marc input decks still work. So if you're using Patran, effectively it would have either had no input version or input version 12 or 11, in which case you'll get the old style Marc input or the older style Marc input. If you're using MenCat, by default, you'll get version 13. You'll see things like the CAD body, if there were CAD models, geometry inside MenCat. You would then see that the finite element mesh is associated with this particular CAD body. Even if you didn't have CAD bodies in your model, on the connectivity section, you'll see something different. It will give you the geometry ID, the material ID, the orientation ID, and the contact body associated with the element connectivity. That was necessary, having to do with this way that we deal with material data files and encryption. So when we have material data, you'll typically not see that list of elements, because that information will have been obtained from the connectivity list. And if you have material data, you can build up your own material data by saying material begin and material end. Give the information, include the table IDs, or in this case, the connectivity said this is material ID 1. Read the data from a UMP file, which meant it was an ASCII text file, or here we read the material data from an encrypted file, and it will basically associate that material with the connectivity, or it will associate that material with the CAD body, and then will have associated the connectivity with the CAD body. So there are definitely changes in the Marc input file, but that allows us to have this really seamless process of going from the GUI, MenCat, to simulations, and then back to post-processing. Okay, well, I want to thank you for your participation in today's webinar. I want to remind people that March 2017 has been released, and it is on the Software Download Center. And I certainly encourage people to look at the release guide associated with this version of the product. Thank you very much.